Okay, I will start the session for week 4. So we have this few concepts before starting with the problem. So this I discussed in the last class also about heat engine. Heat engine, if you see, if you have thermal energy reservoir 1, which is like thermal energy reservoir means it has an infinite temperature. Like the temperature, if it is at T1, it will not go down. So, and if you have a heat engine which is taking heat at from this QH, and it is releasing heat QL by doing some work HC. So an engine, it takes some heat and it does some work for us, and because of that there is a some heat loss QL to the second thermal energy reservoir TER2. So this WHC we can write in terms of the difference between the heat supplied to the heat loss, QH minus QL. So from here you can see that this QH is the input to the heat engine. So efficiency is defined as like what is the output. Output is not QL. QL is the loss, right? We lost that to the other reservoir or the surrounding. So the output we want is the work done by the heat engine, which is like uh, necessary for us. So this WHC by QH will give us the efficiency of the heat engine. So this efficiency eta HC is defined as WHC by QH. So WHC we can write in terms of this heat supplied minus the heat lost. So if you write like that, it will be like 1 minus QL by QH. So this is the efficiency of any heat engine. So if you want to understand this, like you need to understand about the reversible process or reversibility and irreversibility, that I am not going through in detail. But if you have a reversible heat engine working between the same temperature like QL and QH, this is the question in the assignment. So these are some corollary which are derived from the second law. So if you have QL and QH, if you have like two temperature reservoir TL and TH, let's say this is TH and this is TL. So between these two temperature reservoir, if you want to find out the efficiency of the reversible engine, then for reversible engine, if you take two reversible engine 1 and 2, and these are called as a Carnot engine because in the name of the this scientist. So this will be same for given a TH and TL. So that will be seeing in soon. So so if you see here, you can see that the proof that no, like see the proofs. I will show you few proofs in between because that is most important for second law to understand second law. So we need to prove that no heat engine can be more efficient than a reversible engine operating between the same temperature limit. So we have a we have two engine here. One is reversible. Here it is shown as reversible. This is the one say first engine reversible, and this is the second engine which is the normal engine. It's not a reversible engine. So in that scenario, we need to show that no heat engine, this heat engine 2 cannot be efficient than the reversible one. So efficiency we understand how to define. This is like output by input. So output for reversible will be WR as shown here, the work done by the heat engine when we are supplying Q1, that is the input heat Q1R. So this is Q1R. So and for any heat engine 2, it is eta any heat engine is W, which is the work done by the heat engine by Q1. Now what we are saying that this is first one is the reversible one. Once it is reversible, we can think about this heat engine as a heat pump. So heat pump, what heat pump do? Heat pump do the opposite. Like in the opposite sense, we can say that this heat pump is taking some energy from this sink at temperature T2, and it is the this heat pump is supplying this energy Q1R to the source. So in heat pump, this will be opposite. Sorry. So heat pump, this will be opposite. WR will be like the work that has to be done by the pump to supply the energy Q1R to the source. So you can write the COP if you want, but that is not important for this problem. If you want to write the COP, it will come as the output. What is the output here for heat pump? That is Q1R. Always remember efficiency COP, that is defined in terms of output by input. And input is not this one. Here the work done is the input. If you don't put the like this work is which one, like defining this problem, or the heat pump can deliver this Q1R output as output when we do some work on this heat pump. So this work will be WR. So this is the COP of the heat pump, Q1R by WR. So it's just opposite of whatever we have taken here. That is because this is a reversible heat engine we are considering. Now let us assume that we have defined eta NE and eta reversible heat engine as in terms of work done, and in terms of the output versus input, outputs divided by input. Now if we take if we assume that this eta NE is greater than eta R, so this eta R is the reversible heat engine efficiency, and this is like any heat engine efficiency. So let us reverse the cycle. So that's what I told you, because in a reversible heat engine you can reverse it and it can be used as a heat pump. So in that case, the system of this HCR, that is heat pump, now it is working as a heat pump. We can say that this heat pump, whatever heat is coming out to the source, that heat is supplying to the heat engine Q1. This Q1R, if you supply to the heat engine as Q1, so that means this Q1R and Q1R equal. So once that is equal, we can write this definition in terms of WR Q1R is greater than or is less than W by Q1. So now these two get cancelled because they are equal. So we will have WR is less than W. That is the work done in the reversible heat engine is less than the work done in a normal heat engine. Now if you see this work done in the reversible heat engine is less compared to this work done in any heat engine. So if you take the difference, this is what the work is developed by the system, and this work is developed by the system where the system is working such that this is working with only with a single source, like single thermal reservoir. We are not talking about the sink here. If you see, so the heat engine we are reversed as a heat pump, and whatever the energy the heat that is transferred to the source, that heat is given as an input to the heat engine. If you do like that, this is working on a single uh, source, and this is producing the heat or the work done, the output as W minus WR, this heat engine in total. So which the problem with that is, so though that difference is developed by the system between this heat engine and the reversible heat pump or heat engine, and this exchanging the heat only with one reservoir. So this is done only by exchanging heat with the source, and this violates the Kelvin Planck statement of second law. So we have a two statement. I am showing only the Kelvin Planck statement. If it violates the second law statements, then we can say that this whatever assumption we had initially, that is not correct. So the Kelvin Planck statement says that it is impossible for a heat engine to produce net work in a complete cycle if it exchanges, I miss the if it exchanges heat only with bodies at a single fixed temperature. So if it violates the second law, then it this is the process is not spontaneous process. So that shouldn't happen. So this work developed that we have got just because that we have assumed that eta by eta r is not valid, is valid. So from this like logically explanation, we can say that this eta cannot be greater than eta r. So this assumption is not valid. So the proof will go like this rather than going a lot of mathematics. So in the class we talked about this absolute temperature TL by TH we can define in terms of QL by KH, and because of that if you see the heat engine for Carnot cycle or for a reversible heat engine, we can replace QL by QH in terms of the temperature of the two reservoir or the two finite reservoir or infinite thermal reservoir. So accordingly, with eta Carnot will be 1 minus TL by TH, or eta heat engine reversible will be 1 minus TL by TH, and for heat engine normal, that is it will be in terms of W by Q only, or you can write in terms of 1 minus QL by QH. So next, like once we know that like this eta R, that is the Carnot efficiency or the reversible heat engine has to be greater than eta normal or any system. So using this we can prove the process inequality. If you want to prove what is process inequality, again we can take a system with two reservoir T1 and T2, where one we are having the this reversible heat engine, one is the normal heat engine. The same process, the heat taken by the heat engine is Q and R, and the work done is WR, and this normal heat engine is W by Q1. That is the efficiency. So we need to show that for any heat engine, this if you take the integration del qt is less than 0, that is this is known as the process inequality. So we know that this we know already, we have seen that eta r has to be the efficiency of a reversible heat engine is the highest like maximum for compared to any heat engine. So we can simply use the formula 1 minus q2 by q1, that is the heat released by the heat that is input to the engine, and similarly this is in terms of the reversible heat engine, and we know this one we can write in terms of absolute temperature for a reversible heat engine. So we can do that, we can write this is in terms of the temperature T2 by T1. So we know Q2R by Q1R equal to T2 by T1. So once we do that, you can simplify, you can cancel 1 negative sign. If you cancel, the this sign will get changed. So less than will become greater than, then you can arrange this in terms of q1 by t1 and q2 by t2 just to make it in the form del q by t. And here you can see that for a cyclic process, this integration or this summation q1 by t1 is going to is going to be less than 0, and that's why the cyclic integral del q by t is less than 0. So once we know, we prove that this is true by using the second law of thermodynamics. We are using that to prove process inequality. So once you remember the second law and you know that this eta r and eta n are eta r is greater than eta any heat engine, then the other things are simple, like you can connect to that and you can show one by one. Similarly, if you have reversible adiabatic process in an isentropic process, that is very simple, because the definition says that this one, like for normal heat engine, we say that del q by t is less than 0, but for a reversible process this is 0. That is proven from the absolute temperature scale. So using this, we say that if some cyclic integral is 0, that means what, that cyclic integral has to be a point function, right? That point function is defined as the entropy. That is what is coming here. So this entropy is defined by del q reversible by T from 1 to 2. So for reversible adiabatic process, the del qr will be 0. Once it is going to 0, we have del s. If we integrate this, this is also 0. So s has to be constant. So if somebody is saying about isentropic process, isentropic means constant entropy process. So isentropic constant entropy process is same as reversible adiabatic process. So once in the problem it's saying isentropic process, you can assume a reversible adiabatic, and that will make the life very easy. So for reversible adiabatic process, you can write some expression actually, which is known as the property relations, and those property relations you can use and solve problems. So these are the property relation I was talking about. So once it is reversible and adiabatic, you can directly write TdS is equal to du plus PdV, or TdS is equal to dH minus VdP. This derivation is done in the class. This is very simple. This is actually the first law. If you see, it is like the del Q equal to, this is del Q equal to du plus dW or del W. So this del W we are assuming as a PdV work, and this dq we can write, if it is a reversible adiabatic, we know dq by T is ds, so dq will be TdS. That's what is written. For any process we cannot write this. For this Gibbs relations are like for asymptotic process or reversible adiabatic process. So for entropy equation, this is the general equation, because we have delta S, which is given by this, plus some entropy generation, which is get n equal to 0. This will be like maybe generated internally, like internal irreversibility will be there in the system, because of that some entropy will be generated. Please go to the lecture once. Once you go to the lecture, you can understand this better. So can you anyone say what is the correct now, like maybe you have understood what is reversible efficiency of an reversible engine, which is the correct option? Which of the following is the correct statement? All reversible engine have the same efficiency. All the reversible and irreversible engine have the same efficiency. Irreversible engine have maximum efficiency, and all engine are designed as reversible in order to obtain maximum efficiency. Yeah, all the reversible engine have the same efficiency, right? D. Who is saying D? Okay. D is like all engines are designed as reversible in order to obtain maximum. Actually, we cannot even uh, like obtain a reversible process, right? In real life, because of this. This is the problem. This entropy generation will be there in a system always. Like we cannot like what we can say uh, nullify that. Because of that, this D is like not a correct answer, because we cannot design something which is uh, like ideal. So this is not a real scenario where we can if you able to do this, we have solved a lot of problems actually in our thermal sector. But the problem is we cannot go near to this reversible. This is like an ideal concept which is used in thermodynamics to understand the real world problem. Yes, sir. So yeah, some of answers are given. Abhishek Ras. Yeah, it's an answer A, which is that. Any doubt? Yeah, yeah. Uh, uh, yes, correct. Yeah, that is missing actually. So this reversible heat engine have the same efficiency when they are operating at the same temperature difference, because if you take a reversible engine, it is TL by TH. So if we take all this 1 to let's say n, all the heat engine has to operate between TL and TH, then only the answer 1 is correct. Correct. But whatever Narendra has pointed out, this has to be between two same temperature reservoir. Like this is operating between two same temperature, then only it will be correct. Like here like efficiency of a Carnot cycle. Here the option you know I think which is the correct option. Two is also A. It's same question. Like here we are asking about the efficiency of the Carnot engine, where the engine is operating between two temperature T1 and T2. So the formula is eta R is 1 minus T2 by T1. So if you take T1 above, it will be the first option, right? So eta Carnot will be T1 minus T2 by T1. Okay. Okay. So this is the problem which says this is a farmer runs a heat pump. So we have a heat pump with a 2 kilowatt motor. So if it is a heat pump, so we have to supply work to the heat pump. If it is a heat engine, we have to supply heat to the engine. So this 2 kilowatt, whatever is mentioned here, we are running the heat pump with this. That means this is the work. This is whatever the input work you are giving to the heat pump. So whenever you are reading the problem, you just see the subtle differences. Like if it is heat pump with a 2 kilowatt motor, means that 2 kilowatt is running. The heat pump is running by that. That means we are supplying that much of energy as a work to the heat pump. So it should be keep as second hatchery at 30 degrees Celsius. So heat pump is used. I told you this is the output, right? Whatever is like leaving from the heat pump, whatever heat is leaving from the heat pump, that is the output. So if you want to write COP, it should be Q dot H by W dot in. That is the input. This is the output. So it needs to keep a second hatchery at hatchery in some building, like for second they have some farm, and that at 30 degrees Celsius, which loss energy at a rate of 10 kilowatt to the colder ambient temperature. So what happened? This hatchery is leaking the heat. The heat hatchery leaking the heat, right? So whatever, are you able to see the screen? Yeah. So whatever heat is leaking, that has to be supplied from the heat pump. That is why the whatever output from the heat pump has to be at least equal to the whatever leak is happening. Then only the temperature will remain at 30 degrees. So for that, what should be the minimum COP at least to maintain this heat loss, which is 10 kilowatt? If you consider at least this much heat that is supplied from the heat pump, then what should be uh, the ambient temperature that we need to calculate? And for this, what is the minimum COP that will be acceptable for the heat pump? So I told you the COP formula. That's simple, right? That is would be Q dot H by W. But if you see here, you feel like everything is given. Then what should I calculate, right? But you have to calculate. Yeah, is it? It is fine. It is like it is everything is given only. But you need to understand what is like how to approach the problem. So I told you this is Q dot H is 10 and W dot is also given. So which is like we need a 2 kilowatt motor, right? So if you supply this 2 kilowatt motor, then you can find out the if you divide by this whatever the input we are giving to the heat pump, that will be the COP. That is 5. Minimum has to be 5. If you give more, then it is good for like maybe we can increase the QH. Yeah, any doubt? So the COP is has to be greater than and equal to 5. Similarly, we have the same heat pump is there. Now we have a boiler. So there it was simple because we don't have any a flow. So this is like a closed system, you can think of. It is just heat is going out. In a closed system, the heat and work can be like transferred across the boundary, the system boundary, but there shouldn't be any flow. The mass should be conserved inside, like the mass identity of the mass should be there, preserved. But here we have a boiler, which is an this is an control volume open system. So that boiler is connected as the output. That means the heat pump, whatever it is output is there, that is going as like as a heat that is supplying to the boiler. And the boiler is a control volume where we have an input and output. And with this, we need to see what is the problem. Problem is a heat pump receives the energy at the source 80 degrees Celsius and delivers the heat to the boiler. So TL is given 80 degree, and the boiler that operates at 350 kilopascal, and the boiler input is saturated liquid water and the exit is saturated liquid vapor. That line is very important. So what they're saying is the boiler input is saturated water liquid. So if you draw a PV diagram, pressure versus specific volume. So this input and output are like this point. This is input, this is output, or E. So this input and output are, this is the, you know that this is the saturated liquid water, saturated liquid line, and this is saturated vapor, right? That means this temperature you should know. So corresponding to the pressure, and the pressure is also 350 kilopascal. So corresponding to this pressure 350 kilopascal, you should know what should be the saturation temperature. So this is the saturation temperature T that we have to find out, and then we'll know the temperature inside. So TL is given directly. So TL is given as 80 degrees Celsius. You can convert it to Kelvin, and but we don't know what is TH. The TH, the hint is given as the boiler input is saturated liquid water and exit is saturated vapor. So with this hint, we need to find out that at 350 kilopascal, what should be the saturation temperature. For that, we have to go to the table. Are you able to see the table? Okay. So we have to go to the pressure one. This is temperature saturated water. This is in pressure. So it is given as 350. So at 350, 138.8. This will be the temperature TH. So that is the heat pump is delivering the heat at to a temperature at the boiler, inside the boiler, which is 138.8. Okay. So this TH is 138.8. Okay. So we know that now the heat pump is driven by a 2 megawatt motor. So 2 megawatt will be what? It will be W1, W in, and has a COP that is 60% of the Carnot heat pump. So Carnot heat pump means we can replace those QH by W in terms of temperatures. And this TH we know, TL we know. So speed again send this table in. Okay, I'll send the table. So this TH, I will send the table to everybody in the email. So this TH will be we know already, and TL we know. So from this we can find out what will be the heat pump efficiency for a Carnot in Carnot heat pump. And once we know that, we can find out the COP, and you can use the formula Wn by QH, and from that we can find out this I, like what is the maximum mass flow rate. So for mass flow rate, you can write in terms of whatever is outlet minus inlet in terms of the HE minus HI. Again, for HE and HI, these are at saturated point, right? These 2 points. So we need to find out these values from the table. So corresponding to this pressure, we can find out these values. So corresponding to 350 and 138.88 saturation temperature, you can check this HF and HG we need to find. So your HF is 584.31, your HG is 27232.40. So these are in kilojoule per kg. These are in kilojoule per kg. So once you know HF and HG, and you can find out this heat QH in terms of, sorry, there is some lag because of the internet. I hope you are following. So this Q dot H will be in terms of this the mass into that specific enthalpies, right? This specific enthalpies we found out from the steam table. So once you know that, it can be written in terms of the mass into specific enthalpy, it will come as kilojoule. So this specific enthalpy is kilojoule per kg, and this mass unit is kg. Because of that, it got cancelled, and finally it will be in kilojoule. Okay. Once you know what is Q dot H, that is supplying to this system. Now there is no work done here, so we can write the steady flow energy equation for this boiler. So now this thing is that this is given, right? COP of HP is 60% of COP of reversible heat engine. So reversible heat pump. So heat pump COP will be written in terms of TH is the output towards the work done. Work done will be QL minus QH. QL minus QH will be TL minus TH. So that is what is written. Yeah, 4.89 of it is given here. So 0.6, then TH you are writing in terms of this has to be clear, right? This has to be in the absolute scale or in the Kelvin scale. But here we are writing directly because it is a difference. So all these small things you take care. You should take care when you are solving, because these are the things you will undo mistake in the exam. Because other things are easy. You will understand the problem. You know which formula to apply, but you will mess up these units or some this calculation. You will forget this has to be in degree Celsius or in Kelvin scale. This has to be in absolute scale. That's how it is derived. So this absolute scale we have written here, and this difference you don't have to write because it will get cancelled out from both sides. So once you know that, we can find out what would be the mass using this expression. W dot in is also given. Q dot H we are finding in terms of the mass flow rate, and that will be the maximum mass flow rate, 4.89 kg per second. You can go to the this calculation once, but that's how the problems will be like this only. It will be simple, but there is a very good chance that you will do a mistake while solving. Similarly, these are like same kind of problem. Like you're having some kind of leak in a house, then what will happen? You have a refrigeration system. In terms of heat pump, you're talking now. You're talking in terms of refrigeration. So refrigeration and heat pump, the just the opposite, the output and input. Like in refrigeration and heat pump, the output is different. Input is same. Input is like you have to do some work on the system. Then only we'll get the temperature that is needed for the system, right? Because we have this system refrigeration in our household refrigerator. Also we want to keep the inside at some temperature which is lower compared to the outside. So what is important there, that their output is Q dot L. So if you talk about refrigeration COP, it should be output by input. Input is W dot. If you talk about this as a heat pump, then heat pump COP will be Q dot H by W dot. So that is the difference. This is like for heat pump, this is for refrigeration. You just remember efficiency or COP is like output by input. So what is output, what is input, that depends upon the device. So in this problem, an air conditioner cools a house at TLS 20 degrees Celsius with a maximum of 1.2 kilowatt power input. The house gains energy as leak as 0.6 TH minus TL kilowatt, and the refrigeration COP, coefficient of performance, is beta 0.6 beta Carnot. So this is also given in terms of, this will be like, what will be this? So we have QL, so it will be TL by TH minus TL. So this is given as beta is 0.6 into TL minus TH minus TL, and the COP is this much, and so is the values of outside temperature TH for which the air conditioner unit provides sufficient cooling. So we need to find out TH. So the word W dot is given 1.2, TL is given, we just need to find TH. It's easy, right? Everything is given only. You can give, I will give you 2 minutes, you can try and tell me the answer. I will see how many of you getting these questions, like you're able to solve it or not. Anyone having answer? This will be the Q leak. You, if you're having doubt, then you just have to equate this and this. That's it. This is COP I wrote. This is beta only, and this is beta is given in terms of this. This has to be equal to what? 0.6 TH minus TL divided by W. W is given 1.2 kilowatt. Kilowatt and kilowatt will get cancelled, so this will be the thing. To solve this, you will get the answer. TL by TH minus TL equal to, you can put this 1.2 here. This is TH minus TL. It will be coming as a square. You have to take one value which is positive. So that's what I was talking. This 0.6 COP reversible, that is T2 TH minus TL. So this is given. So you can write W in terms of Q dot L TH minus TL by 0.6 T2. Now we are checking that for sufficient cooling, at least the whatever heat we are sucking from the house, that has to be equal to the whatever is leak. So leak is given in terms of THTL, so it will come as a square, and you can solve it. Whatever the value, positive value you are getting, that you have to take 38.77 around this point. Is it clear, this problem? You do the calculation once. I will share the slides so that you are confident in the exam to solve this kind of problem. The problem will be like this only, or maybe somewhere like in some paraphrase problem will be there where you have to solve like two three question in the single like this. One problem will be there. Yeah, are you able to see? Yeah. Okay. So here again one cylinder problem. A cylinder is fitted with a movable piston contain water at 3 megapascal 50% quality. So at which point the volume is 20 liter. So three things are given. One is the volume, one is the pressure, one is the quality. Quality you remember, right? Anybody remember quality? What is quality? Yeah, dryness fraction. So 50% means it is almost in the middle. So this x will be 0.5. So why quality is important? I will show you. Like again here, like these things are given, few things are given, few things are not given. So you need to use this whatever is given and use the steam table, and that will help you to predict the unknown. So the water now expand to 1.2 megapascal as a result of receiving 600 kilojoule of heat from a large source at 300 degrees Celsius. The water does 124 kilojoule of work during this process. So Q that is supplied is given. Your the work done by the this piston cylinder has been is given, and the temperature of this reservoir from where the Q is coming that is given, and initially this temperature quality is given, and the volume is given. So we need to find out the mass of the water in the piston cylinder. The same problem we need to find out the state point. The state point is given initially P1 300. I hope you can see P1 300 megapascal. X1 is given 0.5. This is the dryness fraction or quality. So quality, if you don't remember, dryness fraction is the mass of the this uh, total mass, like mass of the vapor by the total mass. So something like x will be 0, which will be this will be like saturated liquid, and x is 1 means your saturated vapor you're talking about. Now you have V1 is 20 liter, and from saturated water table, so we don't know what is small v1, right? Like capital v1 is your in meter cube unit. If small v1 is in meter cube per kg unit, so if you know these two, you can find out what is the mass directly. So for that, we need to go to the table to find out what is the vf and vfz at 3 megapascal. So we can go there. So what is 3 megapascal? 3 megapascal is nothing but 3000 kilopascal. So these units like conversion I told you earlier, look, you have to be aware of all this. Like you should know kilopascal, megapascal, even in bar, atmospheric pressure, everything you should know. So at 3000, we need to find out what is VF. VF is this one, and this is VFG. So these two values you can use. Quality is given, so we know at that position what will be the value of the specific volume. So that is what we are finding. We're finding the small v1. Once you know small v1, you can divide by capital V1 by small v1 to get out the mass. What is the mass? What is the mass of the water in the piston cylinder? So once you know the mass, next we need to find out now. Okay, this is done. Next problem is to find out the Noise is coming. So next we need to find out the which of the, among the following pairs of thermodynamic properties determine the final state of water. So final pressure is given. Now we need to find out the this U2. So once you find out the U2, then we'll can tell what should be the answer. So finding U2 again, the you can use this expression first law. Q is given, W is given, M you know, U1 you know, U1 like again you have to calculate from the thermodynamic table. 3 megapascal, X1 is 0.5. Use this formula. So any point function you can find out using F plus X into UFG, or V is VF plus X into VFG, or small h enthalpy HF plus X XFG. So once you know all this, you need to find U2. So U2 is, to calculate, it is 2612.58 kilojoule. I'm out of time, that's why I'm going a little bit fast. If just tell me if you're not understanding. So like that you can find out U2. Just first law of thermodynamics. This is a closed system, that's why there's no nothing here is mentioned as like something is going out, mass is going away out of the system. So by reading the question you should know it is a closed system or the open system. If something is coming as an inlet outlet or some changes is happening, mass is increasing decreasing, then you have to take the steady flow energy equation. But if you have a simple system where we are talking about heat input and work is done by the system, then you need to talk about this. We need to take the first law of thermodynamics. Yeah, any doubt? Yeah, 2612. Correct. So answer is B. Then entropy generation, same thing. So you need to find out the total entropy generation. So entropy generation again, P1 X1 is given. So we need to find out what? We need to find out the S1. S1, like I just wrote this formula. Here S also you can find out SF plus X into SFZ. So this SF you know, SFZ you know from the table. These are the value. These are the two value. You can go to the table. You can find out these values corresponding to this P1 and X1, and not X1, only P1. Because it is saturated water, you need only one parameter to find out the values. If you go to this superheated vapor, then you need two parameters actually. Then, but to find out the final this point, you need two parameters because X1 is important. If you don't know X1, you don't know what at what quality it is there. So in that point, you need if you are giving the temperature and pressure also, then also you can it is fine. You know the point. Similarly, state two is given P2 and U2. So you know P2 and corresponding U2, right? So you need to find out at this P2 what will be your uh, like S2, and that again you have to go to the table and find out like corresponding to this P2 and U2 where is the value lie, and you have to do linear interpolation and try to find out. So this is the in mathematical involved, like you have to do interpolation and try to find out what will be the S2. Once you know what is S2, S2 minus S1 will be generation. So this S2 minus S1 is the generation, and this is coming because of this like from the reservoir, like you're taking some heat from the reservoir, 600 kilojoule from the reservoir, 300 Kelvin. So the first term M, S2 minus S1, you know all the values, you just put it, and this is because of the reservoir. So wherever there is a heat transfer process is there, then there will be like some entropy generation. So in the problem, you look carefully, try to find out what are the heat transfer process, and from that you try to see is there a change in the thermodynamic state in the process in the system, then there will be entropy generation. Then if there is a heat transfer in the process, there will be entropy generation. That two are the two important parameters that you read the question and try to find out, and from that you can find out the generation of entropy. And this is the formula like this I wrote earlier. You can check the PPT whenever you get the time. So I'll stop here. Any doubt you can ask me. I will share the this steam table and also the book. If you are following any other book, you can just let me know. Pikenag is a good book you can follow, and the book that is followed by in the course I will send you the book